Hello, my name is Bikash Sah and welcome to my presentation on an individual electric vehicle charging infrastructure. The EV charging infrastructure comprises of four major stakeholders: the electric grid, the communication system, EV charging system, and the EV users. Each of these stakeholders has its own priorities. Although each stakeholder has an interest that could benefit them individually, the interest cannot be fulfilled without proper coordination. The research reported in the literature focus on either of the four entities and doesn't try to converge towards any technological advancement which could optimally benefit everyone. My PhD work attempted to solve the mentioned problem statement. To start with, I looked into the electric grid and the communication system. I solved the requirement for a faster data acquisition rate, reduced the impact of latency, data loss, and errors introduced due to the communication channels in a V2G system. As a solution, I developed an intelligent controller for a vehicle-to-grid system comprising of a fuzzy logic system supported by an artificial neural network and a few decision-making algorithms. The fuzzy logic controller is used because of its simplicity in the modeling for the uncertainty and complex decision processes. It is found that a faster data sampling rate leads to a better performance of the controller by suitably performing peak saving and value filling using the connected EVs. However, appropriate modifications in the V2G controller, such as increasing the number of membership functions in this case, could lead to a better performance even when the data reaching the controllers are at a slower sampling rate. The trained NN helped to perform data integrity check and corrections based on the real-time computation of the tolerance using previous samples. The other major entities, the charging system service provider and the EV users, have a common challenge to fast charge and constrain the degradation rate in the battery for optimal capacity utilization in a longer run. Accurate battery parameters and state estimation is the key solution in which impedance has a significant role. Hence, an algorithm is proposed to estimate the battery's impedance in real time before the start of charging without adding any additional equipment to the charger. However, the battery is an electrochemical device and just studying the electrical characteristic does not satisfy the needs. Hence, electrochemical models of the battery are used to determine the impact of different charging rates, charging techniques, ambient temperature, and operating conditions on the battery's degradation rate. The analysis performed helped to develop a new charging algorithm in which, based on the electric grid loading and users' requirement, the maximum charging rate is decided, and based on the ambient temperature and estimated parameters of the battery, the optimal charging type, like pulse charging with discharge, pulse charging, or constant current, or constant voltage, is decided. Further, the charging rate is also increased and decreased based on the temperature of the cell sensed in the real time during the charging process. All these algorithms proposed, when implemented together, form an intelligent electric vehicle charging infrastructure. The algorithms are tested and verified in a 2 kilowatt charger setup developed in the laboratory. For more information about my work, please follow the following publications. Thank you.